Okay, let's make a start. So, this lesson is going to be going through the final kind of probability that will be introduced to you at some point. I know this will be early for pretty much all of you, actually. Most Year 12s are doing the calculus SAC very, very soon. So this is definitely on the earlier side to have a look at them. But nonetheless, it'll be nice for you to have an understanding of. So this is the topic referred to as sampling and estimation. And one of the things that gets brought up here is that it's very similar to discrete in the sense that everything that we work with is very discrete numbers of things, very specific numbers. For instance, like a dice roll, right? Can it be the numbers 1 through 6? You're never going to roll a half on that dice roll. In the context of sample proportions, basically what we're starting to do now is differentiate between when we look at global statistics and local statistics. Global meaning like across the entire population, and local meaning very specific subsets of that. So there's two key terms that we define in sample proportions, in sampling and estimation rather, which is the difference between the population proportion and the sample proportion. So when we talk about population proportion, we use the letter P in that case, and that's going to be the number of things in a population with a particular attribute divided by the total number in the population. So this is more talking global, like across the entire possible population. Whereas the sample proportion, in this case using P hat to denote that, is going to be the exact same sort of thing, but this time within a local sample of the overall population. Determining what's population and what's a sample is going to differ from question to question, but the context should be at least somewhat obvious as you start getting more and more used to the kinds of questions that come up. So in this first example that we have here, there's a mathematics class. We got 3 boys, 5 girls. All right, that's the background setting of the question that we have. First question, what is the proportion of boys in the class? That's like, okay, cool. Well, there's 3 boys out of a total of 8 students, so the proportion of boys is going to be 3 out of 8. That's your population proportion, because you have this total population of the mathematics class, and we use P to denote that. Subset of that question, a group of 4 students is randomly selected from this class. That selection contains 1 boy and 3 girls. What's the proportion of boys in this sample? Well, under this circumstance, because we took a subset of the overall population, we use P hat to denote the sample proportion. But otherwise it's calculated the same way. How many elements existed in the sample with the given attribute, in this case being a boy, out of the total number of elements in the sample, in this case the total number of students. Any questions on the differences between when we're using P hat and when we're using P? I'll pause for a moment. And if I go too fast, it'll just, raise a hand, pop something in the chat, anything like that. Probably better off you pop something in the chat or hop off mute, because I noticed that I can only see like 3 persons' windows at the same time. I don't know if raising your hand pops you up further in the queue. But okay, cool. So that being the case, now we look at how we solve these sample proportions. This is a lot of what we do. We use P hat in pretty much the majority of what's going on in this particular topic. So first things first, we want to figure out how we calculate a specific sample proportion. So in this case, we have a jar with 4 white, 6 black. 3 balls are sampled at random without replacement. So this should be reminiscent of when we're doing binomial. For those who weren't there for those lessons or haven't had a go at those yet, without replacement it simply means that every time I take a ball out of this jar, I leave it out of the jar. So for instance, I could pick 1 black, take it out, I've now got 9 balls left in the jar. Then I take 1 white, I've now got 8 balls left in the jar, so on and so forth. That's what without replacement means. With that consideration, find the probability that the proportion of white balls is 1/3. So, the first thing to note is that p hat is always calculated by x over n, essentially, where x is the number of things that you want to have, and n is the total number of things in the scenario. In this case, we're told proportion of white balls. So in this case, x is going to be the number of white balls, and n is going to be the total number of balls, or in this case, I've said the sample size. The vast majority of what we're doing in this topic is taking a p hat equation and converting it to an equivalent discrete equation. So if we look at the chapter sections, chapter 17 is pretty much all about converting what's being written in chapter 17 into what would be found in chapter 13, maybe 14. Those are both talking about discrete things. So the good news is the stuff in chapter 17 is only superficial. It's a little bit above what we're looking at in 13 and 14. So if and when you're strong in chapters 13 and 14, you will also be strong in this, because all you have to do is this quick rearrange. Sub in your x value, sub in your n value, and then rearrange. So in this case, you want to get the numerator on its own, essentially. So if p hat is x on n, and it also equals a third, that means x equals 1. Clear enough on the conversion there? I'll pause for a moment. Okay, so the next thing is, how do we calculate probability of x equals 1? X equals 1 in this case just means that I found one white ball. All right, so out of the 3 that I chose, one of them is a white ball. Now, because we're doing without replacement, this is where the binomial type stuff can come into play, or using your counting methods, because counting methods is that reliance on when things decrement over time. And so one way you can go about it is to say, okay, of the 10 total balls, we're selecting 3. So the total number of possible ways I could do that is going to be given by the selections equation. That gives you total number of possibilities. That's your denominator. Now for the numerator, the total number of desirable outcomes, of the 4 white balls, we're selecting 1. Of the 6 black balls, we're selecting 2. And so you just do 2 more of those selection equations back to back. The reason why they're back to back is because you consider them being done in sequence. This is a bit of a revision from the counting methods type stuff. When you have things done in sequence, you multiply across. So this one's going to represent having 4 white balls and selecting one of them. Remember, we have 4 total to choose from. And this is going to be the selecting 2 black balls out of a total of 6. So final probability, here's number of desirable outcomes, here's number of actual possible outcomes. Final answer, a half. You just divide the 2. Desirable divided by total. And since these things are identical, you can therefore say that the population, or the probability of getting p hat equals a third is also going to be the same thing as getting the x equals 1. Now, counting methods is probably on the tougher side for a lot of people. And so one of the things you can do in sufficiently easy circumstances is to literally just count them out yourself. Think about all the possibilities in which you could actually get 1 white and 2 blacks. You can get white, black, 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 white, black, or black, black, white. Right, those are your only possible combinations there. And so you would just manually calculate how to do those each individually. That's if your counting method is on the weaker side. Worth pointing out, because of the nature of what we're doing, it doesn't really matter what order you end up doing these in, they all end up being the same thing anyway. That's not always true in most cases though, so worth pointing out that don't just take this for granted. Like, this won't always be the case. It does sort of pay off to make sure that you are calculating them individually. But anyway, you calculate them individually, which just means, what does that mean? You essentially go through each of the possible scenarios and then imagine what each of the consecutive probabilities would be like. So in the case of doing white, black, black, it means I start by selecting a white, then a black, then a black. Which means if I start by selecting a white, I've got 4 to choose from out of a total of 6. So that's why we have 4 to choose from out of a total of 10. Sorry, because we got the white plus the black, which is why we have that 4 out of 10 there. Because I've chosen one that is without replacement, there's only 9 left to choose from. From there, I'm choosing a black. So when I look back at my total sample size, I notice I'm down 1 white ball, but I still have all 6 black balls. And so when I calculate my probability for the second thing, I still have those 6 blacks, but I only have 9 total left. And then the pattern just repeats from there. We lost a black ball in this case, so we're down to 5. And because we lost a ball, we're down to 8 as for our denominator. This pattern repeats for the other 2 things there. Add it all up, you'll get to the exact same result. Anything to clarify there? It's probably a bit of an easier way of doing it, even if it is a longer way of doing it. Okay. Next up, range of values. Again, we're going to solve this the exact same way that we solve discrete probability. The goal is to take whatever your p hat explanation is, and then convert that to an equivalent x equals thing. So we already knew from earlier that p hat being a third is the same thing as x equals 1, because we had 3 total things to choose from, and so 1 out of 3 means I got 1 out of the 3. So p hat being a third is the same thing as x equals 1. What you can do from there is actually expand your discrete table accordingly, right? So p hat being 0 means x equals 0. You chose no y. We already talked about this one. X equals 2 is going to mean 2 out of 3, and x equals 3 means it's going to be 3 out of 3. Sorry, I just got something caught in my throat there. And so we're basically just taking our discrete tables and marrying that up with the p hat table. The only reason you would really do that is so that you can now stop using p hat altogether and just focus on what you already know, or presumably would already know at this stage. So if you want to go and solve p hat being less than or equal a third, it's the same way that we do for other probability tables, which is you figure out all of the elements that are less than or equal to a third in this column. So that's going to be the x equals 1 and the x equals 0 columns, and you want to add those 2 probabilities together. That's how these tables work. You start with outcomes on the top and the probabilities of those outcomes on the bottom. Whether there's p hat or x, they're basically the same thing. One is a ratio and the other is just the specific number that you've got. Otherwise, the methodology of solving it is identical. So if we know that we have to calculate or add, these 2 together, then the only thing that's left to do is figure out what is x equals 0. Well, in the context of this scenario, if x is the number of white balls selected, then 0 white just means all black. So we want to figure out the probability of getting all black, which you could do counting methods or by the other method we talked about, which is just manually think about the number of combinations. And manually thinking about it is actually a lot easier in this case because there's literally only one possibility: black, black, black. So you go your 6 out of 10, 5 out of 9, 4 out of 8, decrementing the denominator, decrementing the numerator, because you have that without replacement scenario. You get your value, simplify it down. That gets you this spot on the table. Finally, you're just going to add those 2 things together. And that'll be the calculating a range of probabilities. So again, this is basically revision for discrete. The only thing you have to do at the start of this question, once again, is convert your p hat values to x values and then treat it like discrete. Anything to clarify there? We're all masters of it. Nice. That's a summary for that one. Okay. Just like the other types of probability, there are also statistics that are associated specifically with sampling and estimation type stuff. This is where things do start to differ just a little bit more than previously. When it comes to calculating probabilities, literally all you're doing is converting your p hat into an equivalent x. When it comes to statistics, they are slightly different though. One of the weird things that comes up is how you calculate mean in this case. The mean of a sample proportion is the same thing as the population proportion. The reason why is because the terms are talking about the same thing. The mean is considered the average of whatever data set you're looking at. Proportions are also basically ratios, right? So when you talk about finding the average, you're essentially just adding it all up and finding the middle. Whereas, yeah, let me say it in another way. So a statement like saying 50% of students study math is the same thing as saying the average number of students to study math is 50%. These are talking about the same thing. This one is written in the context of like a p value proportion, a population proportion, whereas this one is written in the context of like a mean, where it had some data that it was pulling from. It's just a slightly different context. All I'm trying to highlight here is that these mean the same thing. So if you're told to calculate the mean of a sample proportion, you just need to figure out what the population proportion is. So if we had to calculate the mean of the sample proportion, one thing you can do is ignore what I said, go to calculate or convert all your x values into p hat values, and then do the mean of that, like you would from before. That's one way of doing it if you somehow forget that these two things mean the same. And so all you would do from there, again, it's kind of the reverse of what we did before, which is you know you have a n of 3, and so 0 out of 3, 1 out of 3, 2 out of 3, 3 out of 3 is all of those values. Probability is going to remain the same. When you calculate mean in tables, it means you multiply these two values together and you add everything across. So that's this here. 0 times 1 out of 8 is that. A third times 3 out of 8 is that. Add them all up and then go to a half. That's one way you can do it if you forget that the proportion is the same as the mean. If you do remember this, it saves you a lot of headache, because you can go and immediately know a coin toss is going to be 50-50 split between heads and tails. And so right off the bat, I can just say my expected proportion is a half, 50-50. So this is a fallback. This is if you're able to, for one, remember that they're the same thing, but two, actually figure out and use a bit of intuition to save you a bit of calculation there. Any questions on either of those approaches? Easy. Variance. So there is actually a calculation involved in here. There is a way to prove why the variance is a bit different than how it would be in binomial or discrete. It's there if you want. You don't need to know it. This is on your formula sheet. So I think I'll just leave it at that. And for those who are very math curious, can look into this. There's no need to know that why. You just need to know anytime I want to calculate variance of a proportion, I do p 1 minus p over n, where remember p is your population proportion and n is the number of elements in the population. Standard deviation is always the square root of variance, so you just take that variance equation and you square root it. This is true literally every single time you do standard deviation, whether it's continuous, whether it's discrete, it's always the square root of variance. Yeah, worth pointing out, I think this is also on your formula sheet. They might actually just take for granted that you're supposed to square root the variance every time. I'd have to double check that actually. Yeah, one of the two will definitely be on it. It'll be standard deviation or variance, maybe both. Either way, you'll have something to reference. But okay, how do we actually calculate these things? Well, let's have a look at an example. We have a random sample of 4 items selected from a box of 10 pens. 2 red, 8 blue. Calculate the standard deviation of the proportion of red pens in the sample. So it says proportion. The keyword proportion means that you are thinking about things in the p hat, in a sample proportion way, versus thinking about it in terms of the binomial or discrete way. So that keyword there really matters a lot, because standard deviation for discrete is calculated slightly differently to calculating it for proportion. And the reason why is because your standard deviation is always a measure of spread. The differences is if you're doing it in the discrete way, you're measuring the spread of actual numbers of things. Whereas if you do it in the sampling and estimation way, you're measuring the spread of proportions, which makes the numbers significantly smaller because proportions can only be between 0 and 1. Whereas discrete numbers of things can be from God knows how many. In this case, 10. 0 to 10 will be your possible numbers. But okay, keyword proportion means we're going to be using this version of standard deviation. So first things first, figure out what P is. So if it's a proportion of red pens, then P is going to be the probability of hitting a red pen, of which there are 2 out of a total of 10. P is going to be a fifth. We also need N to calculate our standard deviation, which means we need to figure out how many is in the sample. And so it's worth pointing out that we don't use this N, we're using this N. This is a population proportion. This is the sample size. So it's worth really clarifying that these are calculating off of different N's. That's where it gets a bit tougher. But okay, cool. So we do our standard deviation because, well, now we have everything we need. We have a P, we have an N, chuck them in, solve. Yeah, here's a... I'm not even going to bother going into this. I don't know why I felt compelled to write this. Basically what I was saying is, if for whatever reason... No, I'm not even going to... Just leave. That's so much work. In summary, don't do it. Okay, so we'll ignore that one. Was there anything in here worth clarifying? Okay, we're almost done. The last thing to do is how to figure out an approximate confidence interval. So we saw confidence intervals across all different types of probability. We've seen them how to do them discrete. We've seen how to do them in continuous. This is technically also discrete, but because we're doing it proportionally, again, we're using different calculations here. Now, what's a little bit different here is that this one's using p-hats in its calculation. And the reason why is because an approximate confidence interval in sampling and estimation is actually interpreted a little bit differently to how it is in the other contexts. In the other context, you have, it's basically telling you the likelihood that your value falls between a certain range of possibilities. So for instance, let's say we use the previous example here. A confidence interval would tell us that we are some % likely that there's going to be anywhere between 1 and 3 red pens in this sample of 4. Right, it gives you some sort of upper and lower bound of what's likely to occur in any given sample. Now I did kind of just make it impossible there because there's only 2 red pens. Of course, you're not going to get 3. So let's maybe do it in terms of blue instead. So there's 8 total. We're assuming that any given sample, let's say hypothetically speaking, you could have anywhere from, let's say 1 to 4 blue pens in that box. Just hypothetically speaking, that could be a potential confidence interval. When it comes to approximate confidence intervals, what you're actually trying to do is estimate p-hat. You're trying to estimate what the actual proportion is going to be based on your p-hat values. So it's a little bit of a different nuance there. It's not super important to understand the difference. More so just to explain a little bit about why we're using p-hats here instead of p's like we were before. The only kind of confidence interval we do is a 95% confidence interval. Normally, if we remember from before, when it came to like normal distribution stuff, we're looking at plus or minus 2 standard deviations. So in fact, to put a little visual on that, I will grab probably this. No, actually we'll do normal distribution. Let me grab that. that's this sort of thing. So you'd have some sort of bell curve, and plus or minus 2 standard deviations basically would be like this section of the graph. And the idea there is that approximately 95% of the total probability is contained in this red and blue zone in here. That's what we mean by a 95% confidence interval. 95% of the results are going to be between whatever this is and whatever this is. Plus or minus 2 standard deviations is a bit of an approximate. And so for whatever reason, they decided to go slightly more accurately in methods, and they say, no, it's actually closer to 1.96. So instead of doing plus or minus 2 standard deviations, you're now doing plus or minus 1.96. So the overall concept is the same. The value that they're expecting you to use is slightly off, or slightly different, rather. One thing that's worth pointing out, the midpoint of this interval is always p hat. Right, if you notice, the equation is p hat plus some number of standard deviations and p hat minus some number of standard deviations. So if you have some middle point and you go plus and minus some distance either side of it, the middle is always going to be where you started. The reason why I bring this up is because a lot of the time you'll be given a spread of values. You'll be given some sort of standard, some sort of confidence interval like this, and it'll say, cool, now you've got that, figure out n and p hat from that. All you ever do is find the midpoint of it. So you take your two values. Since we know p hat is always going to be the middle, well, you just do the midpoint equation. Add the two, divide by 2. That's going to give you a p hat of 0.08. So that's why that one comes up. This will usually be a multi-choice in the Tech Active. And usually they only ask one of these. They'll do either sample proportion or the sample size, not usually both. Doesn't really matter either way, because once you solve one, you can immediately solve the other, because you can then use the actual equation. You can use the confidence interval equation now that you have either the n or the p hat, and then solve for the remaining variable. In this case, we have the p hat. So you can either use the upper or lower bound, doesn't really matter, p hat plus or p hat minus your number of values. The reason why you can use either is because you have both. You can use the lower bound value that you have, or you can use the upper bound value that you have. So let's say we use the upper bound. We take this, that's our value, and it's got to be equal to p hat plus your standard deviation term. So you just take the p hat, replace all these p hats with that number. The only number left is n to solve for, or sorry, the only letter left is n, and so when you do your CAS solve, it'll come out. If you choose the lower bound, that's fine. You just put the lower bound in that spot, and you do a minus instead of a plus, because you want to go left of the mean rather than right of the mean. But otherwise, it's the same idea. Any questions about that one? Okay. As far as actually just calculating a confidence interval, you're pretty much just using this equation. All right, so there was it was highlighted over here. It's this equation there. Yeah, just figure out your p hat and your n. Z is always going to be 1.96 because you always do a 95% confidence interval. If they get you to do any other confidence interval, they should tell you what the Z value is for that. Otherwise, there's things you can do on the CAS to get it anyway, which we'll probably look at maybe later. We'll see. Point being, they don't do anything other than 95 anyway. Yeah, so we just take the information that we have from this question. Survey of 1,000 people, so there's your N. Indicated 55% of those survey that exercise on a regular basis. So there's your P hat, right? You got some survey, 1,000 people, 55% of them. You've got your P hat value, you've got your N value. It says calculate an approximate 95% confidence, so we're using Z equals 1.96. Plug and play. That's all it is. Is this it? Yeah, it's the last one. Okay. The last thing that comes up, also as a multi, if I recall correctly, is instead of getting you to just do a specific calculation or solve for a particular variable, they try to get an idea of your understanding of how the equation actually works in approximate confidence intervals. So we're told what the confidence interval is, and we're told that a larger sample of households is selected. So whatever this was, we're going larger, specifically 4 times larger. If p hat is the same in both, what factor will the width of the interval be decreased by? So the thing they're trying to get at here is if you take a larger sample, your confidence interval shrinks because you're more confident about where the value is going to be. Like if you just throw a dart randomly on a dartboard, you've got like, let's call it a 1 in 20 chance of hitting any of the numbers on the thing. But if you see a professional dart player smack that 20 every single time, you're pretty damn likely that you're going to hit the 20, the 18, or the 1, if I remember correctly what those numbers are. Point being that upper 3 slices of the thing, because you're more accurate, you've seen much more data to indicate that it's a lot more likely to fall in those particular regions. That's what this is talking about, but in the context of households instead. So if we increase the sample size 4 times larger, what happens to the width of the confidence interval? The first thing we've got to consider is how do we even get a width to begin with? Where does the width of a confidence interval even come from? And that's going to be given by your standard deviation terms. Because if you have a look at the actual way that you calculate confidence intervals, you start at a middle, and then you plus and minus some number of standard deviations. So the total width of how far horizontally you've gone is dictated by 2 copies of this, which is what we're saying here. So if we go all the way back down, the width of the confidence interval is going to be 2 lots of the standard deviation, whatever that standard deviation is. So that's where we're currently standing. If we are now increasing n by a factor of 4, we now have a separate width, right? Instead of having n there, we have 4n. Let's just call this width 2 instead. From there, you can do a bit of factorization, taking this 4 out the front. Remember, you've got to square root it on the way out, which is why it comes out as a half rather than a quarter. And then obviously that half will cancel down the 2. And so if you compare the 2 widths that we now have, one is clearly 2 times bigger than the other one is. And so if our original width is 2 times bigger than the new width, then the decrease factor is therefore 2. It's decreased by a factor of 2. It's pretty math conceptual heavy. It is a fairly common question though, which is why I thought it was worth bringing up. It comes up enough to where it's worth understanding how to actually manipulate this equation or how to do similar things. Like so, for instance, in this case, it was the changing the n value. Another thing might be changing the p hat value. And so you'll do a similar thing. You start with some initial assumption, you plug in a new p hat, and then you compare where you started to where you ended up. So being able to manipulate these equations is a bit useful. That's pretty much it for lecture. So if there's any questions, let me know. While you consider if there's any questions you want to answer, what I'll do is I'll put in the assigned work for this class. For those of us who are new, it'll come in as a, oh, I've got to close the document so I can actually send it. It'll come in as a Word doc. It'll basically say, here's the questions in the textbook that this responds to, this corresponds to. And then, yeah, you'll have a link in the Word doc to grab a copy of the textbook if you don't already have the Cambridge Unit 3 and 4 textbook. It'll be covering chapters 17B to D, and we've also got a bit on the review chapters in there as well. So grab a copy of that if you don't already have it. If you have any questions before hopping into breakout rooms, feel free to stick behind. Otherwise, I shall open up some break rooms and I'll just sort of float around answering any questions you have throughout the remainder of the lesson. All right, let's give this a go. How many have we got? 1, 2, 3, 4, 5, 6. Cool. Okay. Bang, 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 bang. Okay. Cool. All right, that should be a go. Yeah, let's make it happen. How's it going, Estelle?